Okay, so as I noted, we can generalize this proof system that we illustrated for a very simple special case. We can generalize that to any pairing product equation. Okay, and you get this complicated looking verification equation, but it's not quite so complicated. Essentially, it's the same thing as before, right? So we take the unknowns with a ciphertext that encrypts y's. We take the ciphertext that encrypts the x with the knowns. And then we take the unknowns with unknowns to these exponents gammas. So it's essentially the same as before. You take the ciphertext encrypting the witness and plug it into the verification equation, properly extended to be this 2 times 2 matrix. And then you create 2 proof elements that are going to be paired with GU, and 2 proof elements that are going to be paired with HV, and then you check that this hits the target. And as before, you get perfect completeness, of course, with a lot of calculations, and perfect soundness, again, exactly the same idea. You just try to decrypt them 2 dimensions. Okay. If we're interested, instead of pairing product equations, multi-exponentiation equations, well, they're pretty simple to rewrite. So if you take this multi-exponentiation equation, right, you could actually map it to a pairing product equation where you just take h to these yj's. And then you would do the proof as before, just using the h to the yj as the secret yj element. So that would be, when you work out all the details, the same thing as we had for the pairing product equations. And you could do that with quadratic equations as well, just move the quadratic equation to the exponent. Okay? Okay, so in general, we'll have multiple of these equations, right? So the instance will consist of Q equations over these variables. And the claim is that there's a witness assignment to all these variables that satisfy all of the equations at the same time. Okay, and the full proof is then, okay, the prover encrypts all the variables that are in the witness. And for each of the equations, the prover will generate these 4 group element proofs. And then the full proof will be all of these ciphertexts and all of these proof elements. And the verifier will simply check each verification one by one, right? Where the verifier in every one of these equations, it reuses the same encryptions of the witness, so that's the same ciphertext, but then for every equation it will be different quadruple of proof elements that it uses. And that way we know that when we decrypt the ciphertext, we would, again, get something that fits into the verification equations for each of these equations. Okay, so that gives us perfect completeness, and it gives us perfect soundness, because each of these ciphertexts will decrypt to a unique xy, or g to the xy, and h to h, yj in the case of field elements. And again, decrypting horizontally, vertically will give us soundness. Okay. You could ask, what about privacy, right? Because we are doing some encryption, maybe we are hiding something. And it turns out that actually this is witness indistinguishable in the generic group model. So if we assume the attacker can only do generic group operations, then it can actually not distinguish between 2 different witnesses that might have been used. But we also know in the generic group model, we can actually prove that there's no generic group simulator that can give us 0 knowledge. So it's, in some provable sense, not 0 knowledge. And of course, I promised you something stronger. I promised you that I would give you some 0 knowledge. I also promised that I would work on the standard assumption, just DDH. So let's move on to the last part. How do we get privacy and stronger privacy guarantees, and how do we get those on the standard assumptions? Okay, so what we're going to do is we're going to use an extended setup, a larger, more complicated setup. So it will actually consist of 4 group elements in source group 1 and 4 group elements in source group 2. The ones we have here. Okay, so think of G and U and H and V as the same as before, but now we also have G prime, U prime, and H prime and V prime. And what the prover will do is essentially make some commitments to these secret X and Y. So if we have the same equation as before, okay, these commitments will look like this. Okay, so what's going on here is actually it's sort of like, think of it as a double Elgamal encryption. You're both doing Elgamal encryption with a GU, but then also with G prime and U prime. Okay, so it's sort of like a 2-layered Elgamal encryption. Okay, so for every secret group element X, you will pick R and R prime and do this kind of double Elgamal encryption to give you your ciphertext or commitment. Okay, so the interesting thing is that now we can actually have 2 types of setups. Okay, so before we would always have an Elgamal public key, and well, there's no way about it. It is going to be an Elgamal public key no matter what. But now we can actually have 2 different setups that have a different nature, and this is this binding versus hiding setup. So in a binding setup, what we'll do is we'll pick G prime and U prime as a re-randomization of G and U. Okay, so you basically just take GU and raise it to some secret alpha. And for a hiding setup, on the other hand, G prime and U prime will be, again, GU raised to some random alpha, but then we'll multiply the latter one with G inverse. Okay? And the reason we do that is because now, if we're in a binding setting, okay, this commitment here is actually going to be perfectly binding. There will be a unique X inside it. But down in the hiding setup, we're sort of breaking linearity in the setup. This is not just GU raised to something, but there's actually this nonlinear thing here. And it turns out in that case the commitment is hiding, and it perfectly hides what is the committed X. Okay? So I'll make that an exercise. So let's take 10 minutes and try to figure out why are these commitments perfectly binding and why are they hiding on these 2 different setups. Okay, so let's have a look at these commitments. Right, so remember we have either a binding setup where G prime and U prime is G to the alpha and U to the alpha, or where G prime U prime is G to the alpha, U to the alpha, but times G inverse. Now if it's a binding setup, then the commitment C1, C2 is going to be G to the R and G prime to the R prime, and G prime is G to the alpha, so we get G to the R plus alpha R prime. And the same way we get U to the R plus alpha R prime times X, right? And that embeds a unique X. This is just an Elgamal encryption of X with randomness R plus alpha R prime, right? So it's a perfectly binding commitment. If you knew the secret discrete log between A, such that you use G to the A, then you can actually decrypt this and get out X. But the things change when we're in the hiding setup, right? Because in the hiding setup, we have this G inverse, okay? And what it really makes sure is, if you look sort of under the hood of these 2 pairs, GU and G prime U prime, is that they're not linearly dependent anymore. They are independent. Okay? And if you work out the math here, what you get is, again, an Elgamal encryption of something, but that something is now G to the minus R prime times X, right? And since R prime is chosen at random, that means that now we are encrypting essentially something random, independent of X. Okay? So the ciphertext, well, it's not a ciphertext anymore. The commitment perfectly hides what is the committed X. Okay? If you just see these two group elements, it could be any X inside. Okay? So there's no information anymore in the commitment about what is this X that the prover knows. And that's where the zero knowledge part is coming from. Okay. So let's take the example that we had from before. So let's still say that we want to prove that the pair xy is equal to t. Okay? So now we use these commitments here, right? So somewhat more complicated way of creating C1 and C2 and D1 and D2, but it's still the same thing. We'll still plug them into this equation here with the extended bilinear map and see what happens. Okay, now when we do the math, we are splitting it into different components. Now 3 components. One is GU, one is G prime U prime, and then the 1x part. Okay, so we'll get 3 matrices like this. And then these ones will just keep, but then this one will also expand the second ciphertext or second commitment. So you get 1x to the s with hv and something with h prime and v prime, and then the 1x and the 1y. And the latter one, that just gives us this thing as from we had before. But what we now have is essentially 4 applications of the extended bilinear map, again with different vectors, with GU, with G prime U prime, with HV and H prime V prime. But again, we can, just as before, compute a bunch of group elements that correspond to satisfying all these equations. So everything has doubled in size right now because we have both pi1, pi2, and pi1 prime and pi2 prime and so forth. Same for the thetas. So we'll end up with 8 group elements for this proof of this equation here. Before we did randomization, and we were randomizing sort of a one-dimensional space with a one-dimensional space, right? We had GU and we had HV, and we could randomize them against each other with a bilinear map. Now we have 4 combinations, right? We have GU and G prime U prime, and we can match them up against HV and H prime and V prime. So that gives us 4 combinations, so I'll do some more complicated randomization with 4 field elements, but it's essentially the same thing. We're doing some randomization with HV and H prime V prime, and we're subtracting it on the other side. So this equation still balances out. Okay? And those are randomized proofs is what the prover will send to the verifier along with the commitments to the X and Y. Okay? And the verifier, when it sees these commitments and it sees these proof elements, it will plug them into the verification equation and accept if everything matches up with respect to the target element T. So again, perfect completeness. Just plug everything else into it. It works out. So after a lot of math, you will see that we do actually have perfect completeness. If the prover is honest and the pairing of X with Y is really T, then the prover can convince the verifier with 100% probability. Okay, what about soundness? Well, if it's a binding setup, then remember, G prime and U prime is just GU raised to alpha, and H prime and V prime is just HV raised to beta. So actually what you have here is an El-Gamal encryption of the witness, and also the same here, and actually this one here is just some power of that one. So it actually just boils down to what we had from before. Again, decryption horizontally, vertically will give you perfect soundness. Everything will still, the commitments will now be El-Gamal encryptions, and all the verification equations, so forth, work out the same way as before. So soundness is exactly the same, just written with more complicated formulas now. Okay? But the interesting thing here is really what happens on a hiding setup. And it turns out if we have a hiding setup, okay, then it's actually perfectly witness indistinguishable. So whether the prover had one x and y, or the proof had some other x prime and y prime, it's impossible for the proof to tell which one the prover had. Okay, so let's think a little about why this is perfectly witness indistinguishable. So regardless of which witness the prover has, remember the commitments, they're going to be uniformly random now, right? So certainly the commitments carry no information to the verifier about which witness was used. Now the re-randomization also ensures that pi1 and pi2 and pi1 prime and pi2 prime are uniformly random, right? Because they are going to be randomized with respectively t and t prime and t double prime and t triple prime. And in a hiding setup, hv and h prime v prime are linearly independent from each other. So that just gives you some random quadruple of group elements. Again, no information there about what the witness is, right? Okay, and now turns out, if you look at the verification equation, that if you condition on the group elements that contain the commitments and these proof elements here, then the verification equation actually uniquely determines the rest of the proof, right? So regardless of whether it was one witness or another witness the prover had used to construct it, you would still get the same zetas. Okay, so they as well carry no information about what is the witness. So in other words, there's no way, because of this perfectly hiding property of the commitment schemes and because of the re-randomization of proofs, there's no way that you can tell anything about which witness the prover had in mind. So that gives us witness indistinguishability. Now again, I promised you something stronger. I promised you zero knowledge. It turns out it doesn't actually quite give you zero knowledge, right? The problem is that if you want zero knowledge, you have to be able to simulate, okay? And it's hard to simulate when you have an arbitrary t. And the core of the problem really is that, well, I can't simulate the proof if I don't know some way that I could build up to t with pairings. And maybe I don't know, right? It could just be any t that was part of the instance. But there's a special case where we can simulate. And that special case is when t is equal to 1, right? That makes life a lot easier because now I can actually find a witness. My witness is just going to be 1 and 1, right? Take the pairing of 1 and 1, yes, I get 1. Okay, so it's sort of cheating, but it does make simulation very easy. So if t is equal to 1, sure, I can definitely simulate. I can even construct a witness myself. And now, witness indistinguishability is what gives us zero knowledge, right? Because the witness I just picked out of, say, oh, I'll just use ones all over the place, is the proof I get from that is witness indistinguishable, right? So it's indistinguishable from the real witness that the prover holds, right? And that gives us zero knowledge. Okay, so the simulation, the zero knowledge simulation is sort of like this cheating. There's an easy witness to find, and then it's indistinguishable from the real witness that the prover holds. Okay, so when you put this together, then we have witness indistinguishability, and you can do the same kind of things for multi-exponentiation equations, quadratic equations. So we get witness indistinguishable proofs, perfectly witness indistinguishable proofs on a hiding common reference string for pairing product equations, multi-exponentiation equations, and quadratic equations. And if you want zero knowledge, Well, you have to restrict it and say, okay, the target element is just going to be 1 for all the pairing product equations. Yes?
Why did the 113 break soundness?
Oh, so why does it not break soundness? Right, so, okay, so the very short answer is that in some sense, it is actually a good solution that you find. I mean, one's work, so it's sort of like it doesn't break because it is actually still sound, but just because it's a trivial system of pairing product equations. The slightly longer answer is that when you combine it with multi-exponentiation equations and quadratic equations, where you can actually have non-trivial targets, then the reason it doesn't so you still have, let's see, so in this simulation, you will explicitly know that use the fact that G and U and G prime and U prime are linearly independent of each other. And you would actually, as a simulator, you would know the trapdoor underneath that, and you will be able to exploit that. I'll get to the zero knowledge part of these other equations right now, so you can have a look at those. Okay, so remember, the reason that we needed this 1 in the pairing product equations was just so we could actually find some witness that would satisfy, right? But it turns out that you don't need that for the other equations, and it's sort of interesting to figure out why is it that those equations can actually be non-trivial, and therefore we can actually use this proof system for non-trivial types of equations. Right? So let me just talk briefly about quadratic equations and commitments to field elements. For field elements, we'll do a somewhat different commitment scheme. So we'll be committing using this type of commitments. So we'll still use GU and G prime and U prime. But now when we're committing to an X, we'll take G to the R and U to the R. And we'll take G prime to X and U prime times G to X. Okay, and the same thing for, that should be a Y over here in target group 2. And this, by the way, is why I gave the variables in the quadratic equation 2 different names, right? Because they're all in the same field, they're all in ZP. But I'll be using different types of commitments to the X's and the Y's. So the X field elements, I'll be committing in source group 1. The Y field elements, I'll be committing in source group 2. Okay, so in other words, a commitment is something like G to the U to the R, and then G prime and U prime G to X. Remember, we had these 2 setups, right? Binding and hiding. It turns out that on a binding setup, what you now have is you get G to R plus alpha X and U to R plus alpha X, and then you'll have G to the X. So that would be an encryption of G to the X. Right? So that's perfectly binding, and that will be good for when we do the soundness analysis. If it's, on the other hand, if it's a hiding setup, we've actually set it up such that this G that we multiply here cancels out with this G inverse that we have here. So in that case, now we have GU to the R, and we also have GU to alpha to this X. So regardless of what X is, this R will completely randomize it. And you just get a Diffie-Hellman pair raised to some random R. Okay, so that perfectly hides what is X on a hiding string. Okay. Okay, so how do we build the proof then? Well, take this example here. We commit to the values. We plug them in to this extended bilinear map. Do a lot of math on that. And we get out in the end some proof elements, a pair of proof elements here, pair of proof elements here. So it'll be a 4-group element proof. And this is the verification equation that the verifier will be using to check this quadratic equation. Right? So you get perfect completeness as before by following all the calculations on a binding setup. Everything is an LGML encryption of this G to the X and an H to the Y. Okay, so that gives you perfect soundness. It does not actually give us a proof of knowledge, right? Because what you decrypt when you do LGML decryption is you get out G to the X and H to the Y, but it doesn't actually give you X and Y. You may not be able to compute the discrete logarithms. But it does give you a soundness guarantee. Okay? And if we want to talk about witness indistinguishability, when we have a perfect hiding string, well, if you analyze, these things are just uniformly random powers of GU and HV, regardless of what X and Y are. And these proof elements, they are also uniformly random, conditioned on having to satisfy this verification equation. Okay? And if you look at the randomization, makes this first group element in the top left corner uniformly random, and then you can sort of like use a verification equation to check all the other group elements that they're uniquely determined. Okay, so regardless of what witness you will have, you'll get up the same uniformly random distribution of things that satisfy the verification equation. Did you have a question? Yes, sorry, yeah, I have the double use of T here. Yeah, sorry about that. So this T here is for randomization of the proof, and this T here is the target in the instance. So I apologize for that confusion. Okay, so that shows for witness indistinguishability, we get this nice table of things that we can do. So we just saw that before we had pairing product equations, we could do this with 8 group elements for every equation. If we have quadratic equations, that actually goes down to 2 for each. And the multi-exponentiation equations turn out to land somewhere in the middle, and you pay 6 group elements for those. Okay? So in general, we then have proofs that grow linearly with the number of variables we want to prove something about, right? Because we are committing to every secret group element and every secret field element. And then we pay a constant number of group elements per equation in the system of equations. In some cases, that's actually sublinear, right? Because an instance could be actually very complex to describe. There might be many non-trivial gamma yj's in the different equations. And in that case, the proof could actually be smaller than the full instance. But the proof will always be at least linear in the size of the witness because you are encrypting every part of the witness. Okay, so what about zero knowledge, right? So witness indistinguishability, we get this nice picture. For zero knowledge, I argued that we needed ones here. But why don't we need these ones to be 0? And the reason is that we can do some rewriting. Okay? So if we go back to pairing product equations, right? What was our simulation strategy? Just take the trivial witness, let everything be 1, and that's also a good witness, and we'll just use that as our witness and prove things. And that works well for the pairing product equations because they pair up to 1. It doesn't work quite so well for the other equations, right? Because there you actually want to pair up towards something non-trivial. But what you can do is actually you can rewrite a quadratic equation, and the same thing goes for the multi-exponentiation equations. So you just take this t and move it to the other side of the equation, right? If these sums here have to sum up to t, the same as these sums here. Plus 1 times minus t should sum up to 0. So just shift it to the other side. Okay, now you have an equation which is on the right form, which actually has a trivial target element, and you could imagine now just plugging in zeros and things would work out well, right? The only place it doesn't work out well is here, because this is actually, that's a constant, 1, and this is a publicly known element, right? But the tricky here is then, okay, let's look for a commitment to 1. It turns out we already have a commitment to 1. It's in the common reference string, right? G prime and U prime times G is actually a commitment to 1. It's G comma U to 0, and G prime U prime G to 1. So the way we defined the commitment scheme before for a field element, yeah, fits perfectly, have this commitment to 1. So let's use that default commitment to 1 as a commitment to this 1. Okay, and now we're good to go. Now we can plug everything in, it works, it gives us perfect completeness, it gives us perfect soundness when we're on a binding string. What happens on a hiding string? Well, in a hiding string, it turns out that this commitment here, this still holds, but you can also write it as G comma U to this secret alpha. And then that's actually what holds on a hiding string. Okay. So it actually is, at the same time as being a commitment to 1, on a hiding string, it's at the same time also a commitment to 0. The commitment can be equivocated to 2 different values at the same time. And that's great news for the simulator. Because now this stupid strategy of using the all 0 and trivial witness actually works, right? I can actually equivocate this 1 to instead be a 0. And now I have zeros here, and I have zeros here, and I have a 0 here, and I have zeros here, and it all adds up to 0. So that's where you use the simulation trapdoor. The simulation trapdoor allows you to equivocate commitments to field elements. And you just use that to simulate the proof. And it turns out, because everything is perfectly witness indistinguishable, nobody knows what's going on. Right? Okay, and you can do exactly the same thing for multi-exponentiation equations. So that means now that we actually have a zero-knowledge proof. Okay? The zero-knowledge proof works whenever all the pairing product equations hit the target 1. But for multi-exponentiation equations and for quadratic equations, we can actually allow arbitrary targets, because we can do this, move them to the left and simulate kind of strategy. And it turns out that the proofs are exactly the same whether you think of them being as on the right-hand side or the left-hand side equations, so it doesn't change anything in our proofs. But it just guarantees now that we actually have the simulation property, and it is possible to simulate. Okay, so that's the end of the slides. I have a few more minutes, so I do want to talk a little more about sort of how we generalize this. But if there are any questions so far, then please do let me have them. Yeah? Yeah, right. Mm-hmm. Yeah, so you can think yeah, so the advantage and the power really comes from the fact that you can have two ways to set up common reference strings, and by the decision Diffie-Hellman assumption, those two ways are indistinguishable from each other, right? So think of normal operations maybe the perfect soundness setup. So some trusted third party comes along and says, here's some G, U, G prime, U prime, and so forth, right? Go ahead and use that, and I'll not tell you anything about discrete logarithms or anything else, right? And that gives you perfect soundness for these systems of equations, of pairing product equation, multi-exponentiation equations, quadratic equations. Those proofs are partial proofs of knowledge because you could extract the group elements, but you would not be able to extract the field elements because they would be living in the exponent, so to speak. Okay? And then that setup is indistinguishable from a setup where you have a hiding common reference string, but if it's a hiding common reference string, there's a trapdoor that allows you to open zeros to ones and ones to zeros, and that you can use to simulate. So now you can get zero knowledge simulation because you can just take all zero and this 1 equal to 0 trick, right? And now you can actually find a way to simulate proofs. And when you simulate this with this trivial all zero witness, it's actually witness indistinguishable, perfectly witness indistinguishable from a real proof with a real witness. So that's where the zero knowledge power comes from.
How do you know these trapdoors for the simulation?
Typically the way you would use this is you would use the simulation only in a security proof. So you do some cryptographic construction, you work through, you get the user perfect soundness to whatever you wanted to achieve with that, and at some point you are then saying, okay, look, but how do I know that nobody knows the witness that's being used? Well, I could have switched the common reference string, nobody would have known the difference, but if I had switched it, I could have had these secret trapdoors and the security proof goes through. So you could set up the hiding common reference string with a known trapdoor, and in that case, that's something you have available in an efficient manner. So it is a polynomial time simulation you get out of it. Okay. Yes? So, sure. So I don't think I have a table with that, right? So all of them have a few group elements per element in the witness. So every witness element corresponds to 2 group elements in price, right? Because you have to commit to it. And then for every equation you pay ranging from 4 group elements to 8 group elements per equation. For some specific equations, so you can have some special equations, linear equations, you can actually get an even lower cost. Now, all of these involve a few number of exponentiations per committed element. And generating the proofs is also something that involves exponentiations, which depend really on the complexity of the equation, because there you do something for every sort of element that gets paired or multi-exponentiated. So that is equation dependent, what that cost is. So the cost of the pairing operation, I mean, depends on the curves that you're looking at. Now I'm guessing, I think maybe a factor, I think pairing is 4 times, 5 times the cost of an exponentiation in the target group, which again is maybe a factor 2 times the cost of an exponentiation in group 2, which may be a factor 2 times the cost of exponentiation in group 1. I mean, all ballpark figures. I'm sure those numbers are off, and it really depends on the curve that you're looking at. Okay, so what I really wanted to do with this these lectures here is sort of get into the heart of I think the type 3 setting is what people would do when they do real cryptographic protocols, and sort of how it works, and sort of get you to the point where you could sort of go through the equations yourself. You could build your own equations. The question of saying having a linear equation now is sort of an exercise that I think you would all be able to solve at home and figure out something more efficient than I think the cost is 2 group elements or something like that. Now, of course, you can ask, okay, so does this generalize it? And the answer is yes. You can do this in many other pairing settings, so you can do it in type 1 groups, for instance. You can do it for composite order groups instead of prime order groups. You can do it in the symmetric setting where G1 is equal to G2 and based on the linear assumption instead of the GH assumption. And there's lots of ways you can generalize these, and it all works. So the general picture is that you can translate all these groups and this extended bilinear map to instead think about modules. And then you're really sort of doing equations over modules, and then you're mapping into some super modules with a super pairing, and it all works out, okay? So there's a lot of linear algebra in it, but it all works out, and it generalizes quite a lot. Then there are lots of tricks that one can play to do things a little more efficiently. So for instance, if you're worried about computation, you can save a little bit by when you have a system of equations you want to prove, that you could say, okay, the prover, instead of just going ahead and proving right away, the prover could instead construct a common reference string, prove it's a soundness, a perfectly binding common reference string, and then use that common reference string to create the proof, right? Why would you do this diversion? Well, in some sense, you're just coming up with a different common reference string. Why didn't you use the original one? But the point is that once you've done that, the prover actually knows all the discrete logs in this new common reference string, right? And it might actually save computation in all that kind of work later on. So there are these kind of tricks that one can play. There are also some nice tricks that one can play in setting up these common reference strings, right? So I always said, okay, we trust that we have some trusted third party that comes along and says, here's a common reference string. What if we don't have a trusted third party, right? What if we just start from scratch and there's nothing there, right? In that case, we cannot get zero knowledge, but we can still get witness indistinguishability. So you can still actually, in sort of a verifiable way, set up a common reference string or related common reference string, so you know that at least one of them is perfectly sound. And then you prove with each of these that things are good and correct, and you get a non-interactive witness indistinguishable proof without any trusted setup, because you only use you generate the setup yourself, but it is something that can be verified. So there are lots of these variations you can do and optimization tricks, and people have also looked at various optimizations, sort of how do we batch verify these kind of things, and also for some systems, I've sort of thought of this very much in terms of linear algebra and matrix multiplications. But I think, Julia, for instance, you've been thinking about this in terms of polynomial equations, and you could save something in the computation, right, by doing that. So there's lots of tricks that one can play here. And then the other part is there's also a question of how do you build up an ecosystem around a proof system, right? I mean, so the motivation here was really, sure, we can do NP complete computation, but the real goal here is how do you do concrete cryptographic protocols, right? And it turns out that you can sort of build up an ecosystem that matches this proof system, and we did that. We called it structure-preserving cryptography. The idea was to construct pairing-based protocols where, as much as possible, you only use the generic group operations, and you only use group elements. You don't send field elements, but you mostly send group elements. Okay? So you can build structure-preserving signatures where the signatures and the messages are all group elements. You can have structure-preserving encryption, where the public keys and the ciphertext are group elements. LGML encryption is one example of that. Okay? And when you build these structure-preserving protocols, they really match very nicely this proof framework, right? Because now we only have group elements, we only use generic group operations, everything is nice and clean and works nicely with the pairing product equations we had here. So it turns out that then you can sort of glue these structure-preserving protocols together with Groth-Sahai proofs, and you can start building more advanced protocols based on that. So it's not just about the proof system, it's also about, is there an ecosystem of cryptographic protocols that supports it? And I think I'm running out of time now, so thank you for your attention.